Okay, everybody, we're back from lunch and we're ready to start in with entity relationship diagramming. You're probably not your most favorite subject, but it will be hopefully within the next couple hours. Who knows? No promises there. So what you're looking at is assignment number 1 during the break. I uploaded everything into the EMS except for the PowerPoints. They're not in there yet. But all the assignments are in there. There's 5 assignments. They're worth 10 points each. And they are due on August 22nd. And we have a CSLO essay that's also worth 25 points that's in there as well. And all of the assignments can be downloaded from the EMS as well. So you have everything that you need to finish the course tomorrow if you wanted to, except for that final exam. So what you're looking at here is assignment number 1, and I thought maybe I would introduce assignment number 1 before I introduced entity relationship diagramming because it's on the same subject matter. And I'm trying to make this a little bit bigger so you can sort of see what it looks like. In assignment number 1, you've got 20 pages of reading to do. I know. It's all on entity relationship diagramming, but I'm going to give you a couple hours a lecture on the same content in a few minutes. So you may or may not necessarily have to read through all this. It depends on your background. If you've already been doing this and you know how to do this, then you don't have to read through this actually. Nothing in the reading except for all the information you need to answer the questions. It goes through everything. It's like a book. Everything you ever wanted to know about entity relationship diagramming. If you go all the way down to the bottom of all of this reading, down here on the bottom you see that there is an assignment. It says assignment, complete all 4 parts as described below. Part exercise 1, 2, 3, and 4. There's 4 parts, and what you're doing with these parts is exactly what they're trying to tell you to do here. And this is where I'm going over it so I can kind of give you an idea. Not all of these diagrams can be built. There's some missing information. There's also some information that is a little vague and ambiguous. So as an example, the first one you can build it. It's actually not too problem. It's not that big of a problem. So you want to identify all of the entities, attributes, relationships, and the degrees in the following. Hence, draw an entity relationship diagram. For the first assignment, you're just drawing diagrams. You're not translating them. The second assignment is a simpler diagram that you're going to draw, and then you're going to translate the diagram into a bunch of tables and give me the table structures. So the second assignment brings you through the whole process. The first is just on learning how to do that and gives you practice creating entity relationship diagrams. In exercise number 2, and I'm not going to read the whole thing to you, I'm just going to read you the instructions. It also says draw an entity relationship model for this exercise. Show both cardinalities and optionalities. So in the second one you're showing cardinality and optionality. In the first one you're not. In the first one it only says to identify actually all entity types, attributes, and relationships and their degrees. How many participating? I'm going to talk about all this stuff in a few minutes. So don't worry about it if you don't know what I'm talking about yet. But make sure you read the instructions for each one. They're a little bit different. So put a question mark. Put a question mark where the degree is not clear from the text. And don't assume anything. Rather, write a list of questions you would have to find answers to in order to complete the model. Meaning you can only go so far with this. There's not going to be a right or wrong answer. Depends on the assumptions you make, actually, in terms of how far you're going to be able to go with this. Some of them, like the first one, you can complete it entirely. The second one, there's some questions you need to ask. So knowing the right questions helps you go back. Because here's what happens in the real world. Customer comes to you and says, I need this database, and it has to include X, Y, and Z. So you go back and you build a diagram for X, Y, and Z. And then you realize, well, I don't see the connection between X, Y, and Z. And so you come back to the customer and you say, I got this far. I'm missing this piece of information. And here's the question. You ask the question, you get the piece of information, then you go back and you complete the diagram. Or you go through it again. It's an iterative process. So then you take what you know, try to get through it until you've completed the diagram. So it's a question and answer kind of session that goes back and forth between you and the client until you actually understand. And in the process you've understood and you've learned a little bit about the system and you have more information. better than taking a partial explanation of the system and implementing it without even understanding it, because you're never going to implement what they wanted, because they didn't even give you everything that they wanted in the beginning, most likely. Rarely are you going to get the model customer who's going to practically write it for themselves and just pay you to do nothing. So you're the one who's supposed to be interpreting the instructions and figuring out what you're building, hopefully. So in part number 3, draw an entity relationship diagram for the following. Also produce a list of questions you would have to be answered in order to complete the model. Each one of them are going to have questions. Number 3, draw an entity relationship model stating any assumptions made. So in number 4, this one is workable. So the ones that say asking any questions, you build it to a certain point, then you're going to have to start asking questions in order to answer it. In the last one, you just make the assumptions. By the time you get through all 4 of them, you'll realize that it's not a matter of learning how to diagram. It's a matter of figuring out how to communicate with the client so you can get the right questions answered, so you have the right information so you can complete the diagram. Otherwise, you're going to get partial information out of this. So that is assignment number 1. After this weekend, you should be able to do assignment number 1 and also assignment number 2. Assignment number 2, let's just preview that real quick here. Assignment number 2 is on the same topic, actually. And in assignment number 2, we are taking the concept here. The assignment is designed to help you get some experience and practice creating complete database designs by developing a database scheme and ER diagram, and then translate the scheme into the appropriate tables that go along with it. So you're given a straightforward, I can create this entity relationship diagram. All of the details are included, not partial. So you're given a complete scenario. What you're going to do is design the entity relationship diagram, and then you're going to convert the entity relationship diagram into the relational scheme. And then you're going to specify the key attributes and each entity type, structural constraint on each one of the relationship types. And note any unspecified requirements and make appropriate assumptions where the specification is not necessarily complete, but you're going to make it complete. So you're going to draw the diagrams, you're going to take the diagrams, and you're going to translate them into tables. Interesting thing is, if you go through this process, put the diagrams first, table set second, you're going to get a different set of tables than if you guess at the design. If you guess at the design, you're going to get a different set of tables. In all of this, in the assignment number 2, and also in all 3 scenarios of assignment number 1. So I can tell if you've guessed it. And actually number 1, there's no guessing because you just create the diagrams. But in number 2, you can tell if you guessed it, because you can tell which ones. The tables match the date. It's like the chicken before the egg for which one came first. The tables match the diagram matched the problem description. It's going to be different than if you just, out of your head, just threw some darts and went, oh, I think I need that table, I think I need that table, because it's actually kind of surprising how few tables you actually need. You're going to have a lot more tables than you need if you don't draw the diagram first, which is kind of interesting. So let's talk about diagramming. So actually it's more of an art than it is a science. I will show you an example, but probably not till tomorrow because we have to go through the translation. We're going to see right now, we're going to go through entity relationship modeling. Tomorrow I have an exercise that we're going to do that's going to take and translate, and you'll see how the tables come out differently. Because through process of elimination we can combine tables together if we know what's in each one of the tables and how the tables relate. But we have to go through the entire process in order to get to the point where we're creating those tables. Which probably not realistically, it might happen later today, but most likely not till tomorrow, but we'll see. Alright, so we're going to learn how to use entity relationship modeling and the concept that's based on entity relationship modeling and diagramming techniques, and how to identify and solve problems using entity relationship diagrams. There's 2 problems we're actually going to run into, and the problems are easily solved. Connection and fan traps, where there might not be a connection between one diagram and another one, or there might be multiple, or there might be some ambiguity within the connections. So what you're looking at in this slide here is an example of the finished product. So this is what we're drawing. so you have a visual. So you might look at this and go, oh, it's kind of complicated. It's not really complicated, actually. It's you don't have to. It's not a CAD drawing. There's no artistic ability with this either. And there's a bunch of tools out there that you can use for this. Microsoft Visio works for this. Smart Draw works for this. Actually, all you have to do is come out here and open up a web browser and Google. Actually, Smart Draw. Let's see, Smart Draw. Let's just Google Smart Draw real quick here. Smart Draw is still on the market, but I think they only have like a 15-day trial. So don't install the trial stuff until you're ready to use it. You can draw them out in pen and paper if you want. Don't have to use any tool at all. I've actually seen people do it in Microsoft Word. I've actually seen people do it in Paint. You don't have to use anything. If you want to, you can go up here and go ERD diagram tools. Oops, I just saw it. Diagram software. For the Mac, I can't remember the name of it, but there's a couple of really good. Actually, I've never heard of eDraw. There's a couple of really good shareware, freeware versions. Doesn't really matter what you use. eDraw looks pretty good, but I'm on a Mac system, so I'm not quite sure if that's going to work. But see, you can sort of see what it looks like. You can actually automate it. So some of the, these are entities, by the way. Some of the entity formats look a little different. If you have already done this before, you have a tool you like, go ahead and use it. You can use any symbol set that you want, any tool that you want. I highly recommend doing it for free. There's a lot of free shareware programs out there, or trial versions of programs. It can have watermarks on it. That's fine. Watermarks are like little logos that say unregistered. That's fine. I don't care. Or you can do it by hand, pen and paper. Pen and paper works out great, actually. Or you could do what I did and type in ERD diagram software. And do a Google search and you'll find, as you can see here, there's an abundance.
Not Paint?
Excuse me?
Not in Paint?
You can use Paint if you want. It's kind of a manual process, but you can if you want. You can make it as easy or as hard as you want. But that's what I'm sort of looking at in terms of the generic style. It doesn't have to look like this, as I was saying. You can use different symbol sets, different, as long as it's an entity relationship diagram. This is what we're going to build in the next hour or so. We're building it piece by piece by looking at the problem statements, and we'll put this together and then we'll see how it assembles. And this has all the characteristics of everything, all the scenarios you're going to run into. So going back to this three-level architecture, this gives us our conceptual schema, and the database tables themselves are the internal scheme. So we're looking at from a concept level. This isn't what the user sees. This is what the developer sees from a context level. So we have an art and a science, obviously. Good judgment pulled together with powerful tools creates the end product. Models describe, a picture says 1,000 words. You can read through all the definitions of that. The data model itself is a representation of the real world. And then we have our conceptual, our internal, and our degrees. I'm going to kind of skip through here to the modeling, which starts right here. Concepts of entity. There's only 3 components on this diagram: entities, relationships, and attributes. It's called an ERD, entity relationship diagram. That's what that stands for. Not a data flow diagram. If you studied software engineering, data flow diagram actually is for the processing of the system. Entity relationship models the data of the system, which is interesting because you think data and data flow would be data, but it has nothing to do with data. It's the processing, so it's just kind of weird. All starts with the entity. As I mentioned before, entity is sort of like an object. Entities have types. So, and then they have occurrences that go along with them. So if we take a university example, entity of a student is a type of object. So think of types when you do things, because what you don't want to do is have a grad student, undergrad student, CS student, HR manager student, MBA student. They're all students. They're all entity occurrences different types of occurrences, but they're all of the same entity type. So narrow it down to the type as much as possible. Types are groups of objects. So a group of objects with the same properties. So if I were to create a university entity relationship diagram, I'd have one box that said students or student on it. And I have many instances of students that work through the system. Don't put a bunch, I've seen it before, that's why I'm saying this. Don't put a bunch of students out there. Only one of the same type. And they all have identified by the enterprise or part of the enterprise, and they have an individual independent existence. Students exist whether there's classes being offered or not, actually. So will the faculty, so will the classes. Well, classes exist without students in them, I don't know, but you can think about that one. Entity occurrences is uniquely identifiable objects of an entity type. They all occur in different ways. So here's some examples of more entities that may not necessarily become apparent to you. Physical entities: staff, property, customer, part, supplier, product. Conceptual existences: the sale. A sale is an entity. Work experience is an entity. An inspection, a viewing, is all occurrences of entities. A view, a viewing, and inspection. So let's look at a banking scenario. Here we have an entity relationship diagram of staff and branch. We have staff that works at a branch. So we have one box that says staff and one box that says branch. So if I were writing a couple of entities, as I mentioned for the university example, I'd have one that says students and one that says teachers. Maybe one that says classes. So what a lot of people like to do in the beginning is just identify the entities. So we have students, teachers, classes. You just go through your mental list. In fact, some people like to brainstorm it. And what they'll do is they'll write a list on a piece of paper, and then they'll go through and they'll say, you know, oh, grad students, undergrad students. Oh, wait a minute, that's just students. And combine entities together. So we have teachers, TAs, assistants. Isn't an assistant a TA? Okay, yeah, combine it together. So if you can get rid of the extra entities before you even start the diagram, you're in good shape. Most likely you have more entities than you need in terms of the concept. So all the entities have a name. This is in all of the diagramming tools, by the way. They always will have a name associated with it. This generally turns into your table name further down the road. And then we have an entity name that just goes in the box. This is for illustrative purposes, this little description. So we have an entity type, which is a set of meaning of associations among the entities. And then we have the relationship relationship type and relationship occurrence. The relationship type is how they're associated. The occurrence is the association, which includes the occurrence from each participating entity type. So what does that mean? Here's a has relationship. And the relationships are probably the most problematic because people get confused and go, oh, what should we call this relationship? How about has, have, is? So keep your relationship names, and you want to name each one of the relationships because some of those relationships turn into tables. And then you have to wonder, what's going to be the table name? Works for, works, performs. Think of all of the adjectives you can possibly imagine to describe what people do and how entities might have a relationship with each other. So in this example, a branch has staff. So we're going to use has. And this again is actually out of the recommended textbook that I gave you. And this is a diagram, not an entity relationship diagram. It's a traditional dependency diagram, actually, showing you the components. So the one in the middle is the relationship. And you notice that the author has put a little arrow here showing that the direction of the relationship goes this way. So the branch, which is an entity, and the has relationship works with the staff, which is an entity. And here we've indicated staff number and branch number as the components that have the relationship. So here we have in this diagram here the branch B003 and B007. These two branches have 1, 2, 3 relationships. Why? Because branch number 3 has 2 relationships and branch number 7 has 1 relationship. And those relationships are with 3 different employees, SG37, SG14, and SA9. But that's not an entity relationship diagram. If we were to write it as an entity relationship diagram, it looks like this. That's the entity relationship diagram component. So that's what I was saying before. We can go from dependencies, a little bit more confusing, actually. Dependencies are those buttons and the arrows, bubbles and the arrows. And we can put it in an entity relationship. And this one says it has staff relationship. So we have a relationship name, in this particular case, that's showing up on a line. This is what's called a binary relationship. It has a 1 to 1, 1 and a 1 for 2 for binary. 2 participating entities in one relationship. No diamond symbol here, which I've seen it before, and it's proper to put a diamond symbol here as well. You can do that. It's not a problem. If you put a diamond symbol here, you put has inside of the symbol. And I have it written out in a couple more slides from now. Now the arrow is going this way. There's no law that says the diagram has to be read left to right, right to left, top down, bottom up. Read it any way you want. This one is purposely done backwards from regular English. If you speak English, you know you go left to right with a sentence. So I would go staff has branch. Man, it has a staff have a branch. Doesn't make any sense. Well, the arrow is pointing this way, which means you're supposed to read it from here. Branch has staff. So why do we pick has? She can say contains. Branch contains staff. Branch employs staff. If we wanted to turn it around, I could say that staff works at branch, or staff employed by branch. It's optional. So that's why 2 people won't create the same diagram. You won't think that way. You might not think left to right. You might think right to left. You might think differently. This is correct. I can make about 4 or 5 different variations of this. They would all still be correct. So branch has staff. This is for illustrative purposes. This is the name of the relationship. These are the 2. Be generic as possible with it. And know that you can read it left to right, right to left. But the word here is meant to go in the arrow direction. You don't actually have to put an arrow in there if you don't want to. So you could say works. Branch works staff. I don't know, but staff works at branch. So sometimes the name of the relationship isn't going to make sense English-wise, read both ways, but the logic should. There should be the association works both ways. Now we have the degree of relationships. This, I said before, is a binary. 2 participating entities. We have binary, we have 2, 3, 4. We're not going to go past 4. If we go past 4, it gets kind of confusing, and then you break it out into a separate diagram. So 2, 3, 4, pretty typical. 2 is actually quite common, actually. So here's another 2. Binary relationship called property owners, or peons. P-O. I don't know. Kind of an interesting relationship. And this is what happens with some of the relationships, actually. You can take this approach if you want to as well. So it's really property owners. So, you know, you can make some word up. It doesn't have to be a real English word. Don't put a number there, put a word there. If you start putting numbers on here, then it gets confusing because, you know, what's number 1? I don't know. POs, I can go, oh, property owners. So, or you can do like what you do with variables, you know, number, NUM1, first name or something, I don't know. You can make up names. So private owner owns property for rent. So private owner, property for rent, and P owns goes in this direction. So private owner owns property for rent. That's 2. Let's go 3. This is where the diamond comes in. So for a 2 binary relationship, no need to put a diamond symbol in there. For 3, that's where this diamond symbol comes into place. So now we have staff that register branch with clients. So staff registers a client at a branch. So I can go here. Staff, I originally started here. I said that staff registers clients at a branch. Actually, I said staff registers at a branch with clients. So all three of these people are participating in the same relationship. Or I could say branch registers with staff and client. Or client registers with a staff at a branch. All three are participating in the same relationship. This is different than if I wrote two separate ones. If I said staff registers branch and left out client, that's different because there's no mention of the client in there. Or staff registers client with no branch. Leave the branch out over here. Basically turn this into a binary instead, which can easily be done. It turns into two binaries. Actually, you can get three out of it actually. You can go client, branch, staff, client, staff, branch. Is it all going to mean the same thing? No. And it leaves for ambiguity. So this is actually the backward way of doing it because usually the customer is going to give it to you in 2 or 3 different, and you got to put the pieces together and say, well, where does the client register with the staff? At the branch. Oh. And then you have the pieces together because otherwise they could register it at home over the phone. So yeah.
Why are we not showing arrows in this?
No arrows because there's no direction. There's no flow.
No.
In the previous one, we had a flow because we only have binary and an arrow. In here, we have 3 participating relationships all working in a circle. The staff is registering clients at a branch, or the branch is registering staff and clients together, or the staff, the branch or the client's registering at a branch with a staff member. So it reads all directions, so there's no intended arrow. However, most people would go left to right, which is how this is written. So we start with the far left, and then we move to the right. So that's 3. And as I mentioned before, we can go up as high as 4, and that's how the diamond gets turned into the diamond. That's why the diamond symbol is being used. So here is our 4 participating entities all in one relationship. You see it naturally lends itself well to this diamond symbol. Now we have a solicitor that arranges a bid on behalf of a buyer supported by a financial institution. Do we really want to put more into that sentence? Nah. This is as high as level as we go. If you start putting in more than 4 participating entities, then it's like too convoluted. It's like, wait a minute, just break it out. So this is easy to program in. So a solicitor arranges a bid with a buyer at a financial institution. Now, a financial institution arranges bids with solicitors and buyers. And a bid is arranged with a buyer and a solicitor at a financial institution. So it works all the ways around. If we break it out and we just say that the financial institution has solicitors, does it really tell me about the bid and the buyer? So at most, you're looking for this. You're looking to put them all together. You put them all together, then you utilize the relationship. When you start creating multiple relationships, and this is partially answer your question, when you start creating multiple relationships, you get duplicate relationships. And so you'll end up having, when you translate this, and not to move too far ahead, but when you translate this into entity relationship diagrams, into tables, each one of the entities turns into a table, and each one of the multi-valued relationships turn into a table. So that's 1, 2, 3, that's 5 tables right there. If I broke it out into 6 different relationships, then I got 12 tables. Then I'm going to have to reduce down to 5 through process of annihilating. So the less you want to combine, the more work you have to do at the tail end. So the first step is to create these diagrams. If you want to be, let's just go simple, create them all like that, you're going to have 2 or 3 times as many tables because you're going to have duplicate relationships being shown, and then you have some sort of weird connection between all of them until you figure out, well, what is that connection? What's that? And then you end up with a smaller number of tables. So either you do the work here or you do the work in the translation. One point or another, You have to think about the combination of the data. So, not all relationships turn into tables, however. There's rules with that. They have to be multi-valued. I'm going to talk about cardinality first. So if they're not multi-valued, then they don't turn into tables. And then if you're doing your translation correctly, then you end up with too many tables. That's the problem that you do when you throw darts and you don't do diagramming ahead of time. You miss the tables that you need. You don't see the relationship tables normally, because you're just throwing darts and you're looking at entities and you're focused on the entities, but you're not focused on the relationships between them. So you never come up with, 9 times out of 10, unless you're really good at it, you're never going to come up with the relationship tables. And if you do, you're going to come up with the wrong ones because you don't know the cardinality. Because you can't have the table to look at. Again, you can't see it from a diagram. So the diagramming helps you understand the problem scenario so that you can get a better feel for what tables to create. After you've created about a dozen or so diagrams and you've done them for production systems, then you stop diagramming because you don't have to anymore. You already think like a database developer, so the diagrams come naturally. And you think in the form of the diagrams and you just create the tables from it. But it's not a bad idea to document it, only because eventually one of these days down the road, someone's going to know, what table is that in? Isn't it much easier to show them a diagram than it is to show them 25, 30 pages of SQL scripts on table creations? You know, the diagram is a lot more user-friendly. And if you're going to do it anyway, you might as well document what you're doing, because you don't want to go through and look at all your table creation scripts and everything. That's going to take longer than you just look at the diagram and go, oh, you know what, the solicitor is connected with the bid. It's through the ranges relationship. Ah, so there's a key here and there's a key here. Ah, already know that. Don't have to go back and reinvent the wheel every time you're going to want to fix a problem. Or add another entity to this. If you have this and you want to add the other entity, this is a lot easier to look at, to know where that table belongs and what needs to be in that table. So. Relationship types. We also have recursive relationships that you never see until you do the diagrams. And then you end up with multiple redundant tables when you don't do this. So recursive relationship types are the same entity type participating in one or more relationship in different roles. So you got multiple roles of the same type. Imagine staff at the branch. Some of those staff are managers. So the person who doesn't do diagramming will have a manager's table. When really it's a recursive relationship. It's not an extra table. It's just a relationship on the table. So the relationship may be given a role name and indicated purposes of the participating entity type plays in the relationship. Here's the supervises. It's the recursive relationship called supervises. So we really only have one entity, but we have two roles. We have staff, so is also a supervisor, and the supervisor is a staff person as well. It's not a different staff person, it is a staff person. So staff, supervisor, supervises, staff, which is the supervisee. And we put the role name down here. So staff. In fact, recursive relationships could look like little bubbles to themselves. A lot of people would draw, instead of these like sharp lines, they just draw like a little bubble. It goes this way. That means the entity has a relationship with itself. It makes it recursive. Because one staff's a supervisor and the other staff is a supervisee. Not a different entity. All the same, belongs all in the same table. Unfortunately, though, I can tell you about 90% of the time you go out to look at, you see managers tables. And then you see TA tables. And then you see supervisor tables. It's like, why do I have an extra table for this? Aren't they all employees of the company? Couldn't you just put role in their column, a column to indicate who they are inside of the table? But no, you have to, and there's like, oh, then they get fired from one, but they're still in the other. So then they're in multiple tables because they're multiple people. I mean, they have multiple roles that they play. Every other Friday, they're the staff manager.
But if you use a unique key, can't you delete it from all the tables? So
Excuse me?
if you use a unique key.
Unique is different. Unique just means it's not a key.
Or a primary key, let's say. Not like a employee ID.
Yeah.
delete the person with so and so employee ID, so then it deletes it across.
But why store them in multiple tables?
That's true.
It's redundant data. And if you're thinking about thousands and thousands of employees, it can get kind of time consuming to do a database search. And how do you know what table to search from? How do you know what that person is? If they're a staff person, then you put an extra attribute in here that becomes part of the recursive relationship key that is used just for the recursion. So. And we'll get into that when we translate that, actually. We are going to translate something with a recursive relationship. So now we have entities that are associated with two distinct relationships. So now we have multiple relationships between the entities instead of a single relationship. So this is the single one we started out with, the has, the branch that has staff. Well, now we have staff that manages a branch. Well, one staff might manage many branches, or many staff might manage different branches. We haven't talked about the cardinality yet, but we still have a manages versus a has. So you can draw more than one line between the entities to signify multiple relationships. If you have multiple relationships, your keys are different. Your keys are going to be different combination of keys than if you only have a single relationship. And it's not a secondary key either. So let's see, entities associated with two or more distinct roles. So manages, branch office, manager, and branch office. That's going to have a manages relationship. And the member of staff and branch, we have the role name. So branch office has members of staff. So we have both relationships indicated in the same diagram. Last but not least, after we have identified the entities, we've identified the relationships, and then we look at the attributes. The attributes are properties of an entity or a relationship type. Those are the columns that you're going to get. So your relationships and your entities give you your table formats. Your attributes give you the information that's going to be in the tables, your columns. And so we have the attribute domains that allow values from one or more attributes. We have single attributes, and then we have composite attributes. So the single attribute is composed of a single component with independent existence. First name, last name, date of birth, single attributes. Composite might be a attribute that's composed of multiple components, each with an independent existence. What about first name, last name of a dependent?
Name.
Yeah. So you combine the dependent with the employee they belong with. That's a composite attribute. You got a bunch of dependents in there. You got child A, B, C, D, E, F, G. How do you know what parent they belong to and for the health insurance policy? You don't know. Which is actually kind of interesting because there's a ton of databases out there, and that's actually called a weak entity. You put weak entities in. They don't realize that they're weak. They put them in as strong entities. They contain no composite attributes. So the children are still on the health insurance policy, and the company's still paying for them long after the parent has left the organization. And they get the bill like, why do we have all these kids on here? And the parent's gone. And then they look at the health insurance, oh, maybe we should revamp this. So then they just close the policy completely, start up a new policy, have everybody sign up fresh. Because they have people, or they have employees on there. It's kind of like the Comcast. It's kind of like the cable companies. They used to have it listed by address, and then they went, oh, let's not list it by address anymore. Let's list it by individual. And then there was no composite association between the address and the individual. It still happens today. You can move into a brand new apartment and have cable service. Because they disconnected it for the user, but they didn't disconnect it at the address. And they don't know, they don't want to disconnect it because they're, who know who lives there? So now they're getting smart so they can shut the, but years of free cable because of no composite attribute. They can't put the pieces together. And years of free medical service. Actually, you can still sometimes quit a company and still keep a cell phone policy. Still keep a cell phone, still keep computers, still keep health insurance. The expensive stuff they're cracking down on, they're just monitoring that manually, but the database could do it for you. So So we have single valued and then we have multi-valued. So this was simple versus composite. Single is an attribute that holds a single value for each occurrence. Multi-valued attributes hold multiple values. Wouldn't that be like a student who takes classes? If you had a single valued attribute, it would say class. So student A could take one class. B could take one class. C, one class. How much you want to bet we have that set up here? Then we have multiple entries for each one of the students in there. I'm just guessing. When really it's a multi-valued attribute. It's kind of like when you see color 1, color 2, color 3, color 4. They take in a multi-valued and they put it into single-valued attributes. And so now you only have 4 color choices. Or you can only take 4 classes. You can only take, so. If you had multiple, then it holds another value. That actually turns into a separate table. So your multi-valued attributes turn into separate tables. Because it would be student along with list of courses the student might be taking. And then it's linked together with the student. We also have derived attributes. Everyone's afraid of derived attributes as well. So a derived attribute represents a value that is derivable from values of related attributes or a set of attributes, not necessarily in the same entity type. Wouldn't GPA be a derived attribute? And the GPA would show up in the table, and it would be derived at each entry point of all of the scores that were recorded for final grades for each one of your classes, instead of having to do a query. So I guarantee it they have derived attributes for GPA, I would hope. So I'm pretty sure that is the case, otherwise it's too long to search to create a GPA score for everybody. And then depending upon when you searched it, when the system was updated, you're going to get a different number. But if they derive it, then it's constantly updated. It never changes. So now we have the concept of keys. Yeah?
Tell me about single, multi, and again, inclusive.
So a single valued attribute would be when there's only one value that can be recorded for an attribute. As an example, date of birth. You only have one date of birth. So you're not going to have multiple dates of birth. However, as a student, you're probably going to be taking multiple classes. So if we had one column that said date of birth, one column that said class, date of birth would be a proper single. Class? It's going to be a multi-valued attribute that's going to be represented in terms of holding multiple values. It's going to be a separate table that's going to have a code in it. In fact, the table itself is stored outside of the student table. And in the table, it would say, if your student ID was 11, it would say 11, SCN this, 11, SCN that, 11, SCN or CEN something or other. It would have a whole list of those attributes, and you'd search it separately. Okay, you can't store a multi-valued attribute in a single value attribute column. It doesn't work. But you have to acknowledge that it's an attribute. If it's an attribute, then it has to be stored as a multi-valued attribute, which is going to be in a separate entity type.
So composite is a multi-valued.
Composite versus simple. Simple would be student ID. If ITU gave tuition discount to all of your dependents, that'd be nice. Then in the dependents table, you'd have a composite. Composite would be a new student ID for the dependent plus your student ID to know that it belongs to you. So if you go through the concept of the health insurance, that's how it's usually done. Employee A has health insurance at the company, and employee A has 2 dependents, Bob and Mary. So it'd be Bob A, Mary A, to make that composite, which is a combination of 2 attributes instead of just one. If I just put Bob and Mary in there, I have no idea who they belong to. And if there's no connection, when I recursively delete A out of the system after A's been fired, I can't get a hold of Bob and Mary. They stay in the system. The last thing we want to do is cancel insurance for people, because then they're going to get into a car accident, they're going to sue us because they thought they had insurance and we canceled it, and yada yada. Too many problems, they just leave it alone. So if there's no connection, there's no composite. Composite is a combination. If there's no combo, there's no way of getting at the parent, and vice versa. If you go through the parent, we don't have no idea whose dependents are in there. So in the old days, they just add people in. Oh, you're dependent, you get added. You're dependent, you get added, without creating a composite key. Generally, the composite is in the weak entity, which is going to be the dependent table. The weak entity is going to have the composite because we need to be able to link that one up to the strong table, which is going to be the employee. They call it weak and strong. Weak doesn't exist unless there's a composite relationship with a strong. Everything's a strong unless you're weak. Strong means you have an independent existence regardless of anything else. Weak means you don't have an independent existence. You're not supposed to be in there unless you have an association with another entity. If there's no association anymore, you're not in there. You're a weak link. Did that help? Okay, good. And derived would be age, GPA. You can store them as attributes, actually. A lot of student IDs are supposed to be derived as an incremented index or something, or as a counter would create a derived ID out of the system. So every time you put something in, you get an update on the derived key, so it's one incremented or something. Lo and behold, the keys. What are the keys? We've got candidate keys, primary keys, and composite keys. Everyone looks at this and goes, I don't understand. I see primary key, I recognize that one, but what is a candidate, what's a composite? It has to do with normalization. So the normalization technique uses the other two. The one in the table that you're going to see a lot of time is this primary key. So I'll start with the primary key. Primary key uniquely identifies the row. So the candidate key, it's a candidate key. I'll talk about that in a few minutes. It's selected to uniquely identify each occurrence of an entity type. So all students, you have student IDs. That's a primary key. A candidate key is the minimum set of attributes, that uniquely identifies each occurrence of an entity type. They use the word candidate because this is what we're going to choose from. If we have too many candidates, we have too much confusion. Because everybody knows, well, not everybody, but when we get starting into the SQL query language, if we have too many candidates in that table, although people think, more to search on. No. You want to make it so they only have one thing to search on. Don't give them too many choices. As an example, we have student IDs. What if, and we decided that the student ID was the primary key. And then we say, well, what about social security numbers? That is a candidate key. Candidate keys are bad. Bad for searching. Because now we got somebody, everyone's got a student ID. Everybody has to have a student ID because it's a primary key, which means the value cannot be null. Anything in a table that's marked as a primary cannot be null, cannot be empty. It has to be unique, which means everybody has to have a different one. That's the primary search mode. You start introducing candidates in there, and it's just like the word says candidate. Well, it could be this one, it could be that one. If I looked at a table and it said passport ID, student ID, social security number, let's pick another one, I don't know, visa number, all those are candidates. Which one is what am I supposed to query that table for? As a user, there's a red flag that's coming out to me as a user. I'm like, well, there's way too many things to search on here. I'm going to get 5 different counts, depending upon who's got a social security number. And why are we going to put a social security number in there when we have a student ID number in there? So you pick out of the candidates which one you want. You get rid of them. You get them out of the system. Don't leave them in there. It's not good. More is not better. More is problematic. You give the database developers, the application developers, too many options to search on, too many different things, too many problems. Too many problems. Only have one primary key of all the candidates. Composite key is different. Composite key is a candidate key that consists of 2 or more attributes. Why do you want to do that? Because you're going to have a multi-valued composite attribute. If you have a composite attribute, it turns into the key. In that dependence table, that should be the key. The key is this employee ID plus this dependent ID, or something about the dependent's first name. So it says employee A dot Bob, employee A dot Mary, employee A dot. So you have the two keys to select from in terms of the composite. So you can go, let's give all of employee A's dependents. Here we got Bob and Mary. Delete them. This works, the composites work for the keys when you do what's called cascading deletes. When you want to get rid of all those dependents, you can cascade them through the keys. If you don't have the keys in there, you can't cascade them. You gotta manually. I remember Bob had this daughter, didn't she? Didn't he? Or employee A, didn't it? I thought they had three dependents. No, they only two. Then you gotta go manually go in there and delete them, which is what people do actually. Doesn't make any sense actually. But a composite key comes out of that multi-valued attribute that is both primary and a foreign put together normally. But we'll get into that in a few. It consists of two or more attributes. It's a composite. You don't put a composite in when you have a primary and you don't have a weak, strong relationship. That's the other thing people like to do. They make this key in here. You've got the first name, you've got the last name, and you have the last 4 digits of the social. So then they make a composite key that has the last 4 digits of the social and the first 4 characters of the last name. And they put it in there as a key. It's like, why did you do that? It's a composite key. It comes out of 2 or more columns. But it's an extra piece of data that you have in there that only got calculated once. And then the person gets married and changes their last name. Now they're in there and you can't find them. Because you work on the logic, well, we have the last 4 of the social. What's your last name again? And they keep looking for you. Oh, you're not in here. Well, I was. Oh, did you get married? Oh, okay. You know, did you change your name? Or some people change their address. Some people use the address, the street name of the address, the zip code. Interesting combinations. They never seem to work out properly, especially if you have a primary key. Use the primary key. Don't make a composite just for the sake of making a composite. So here's our entity relationship diagram of the staff and the branches and their entities and their relationships all put together. So this is now looking more like an entity relationship diagram. What do? We made the box a little bigger. We put, instead of just staff and branch, and this is the 2 relationships we saw on the previous slide if you remember, made the box a little bit bigger, added a little area for attributes, and now we listed them. And then in here we selected with the PK for primary key. So we know that we have staff number, name, position, salary, and then we have this line here to note that this is a total staff. This is a derived attribute. So as we keep adding staff into the table, the total staff keeps changing. So now we have 5, now we have 6, now we have 7, now we have 8. Why do we want to do that? We don't have to. We could actually just derive by doing a query on the staff if we wanted to. But we could use that numbering system for something if we wanted to. It's just an example of a derived attribute. In this case, I don't know if I'd do it that way. And then over here we have a composite attribute. This makes sense. The composite is the address. What's the address? It's street, city, state, zip. Otherwise, if you keep it all separate, there's no way of putting it all back together. Sometimes when you create a composite attribute that has 4 or 5 different sections to it, you can put it all together. Some people like to do the name composite, first name, last name, all name. But it's so small, you could just do first name, last name. So. Here's another multi-valued attribute with a telephone number that has a prefix, a country code, a suffix, multiple values that are stuck in there together. Instead of a composite, it's just multiple things that are put in together. So you can look at that and go, oh, what's the area code? Pick everybody out from area code 408 or something. So anyway, this is what the diagram looks like. It looks the same as before. We just added these 2 sections of the boxes down here. We elaborated the boxes a little bit. Here's our strong and our weak. So the strong entity that is not existent dependent on another entity. An employee for a company is pretty strong. But dependent on one of those employees, not so strong. So the entity type that is existent dependent, if employee A is not working for the company, then their dependent's not going to be on the health insurance, I hope. So that's the week. So we have a strong entity type called the client and a weak entity type called preferences. You get this a lot with web development. Not everybody who signs up for something is going to put in all of their properties. Actually, you know where you're getting this now is with, you ever go to I just did this the other day at Orchard Supply, actually, the little hardware store down the corner. I wanted to buy something. I'm like, do you have an Orchard Supply account? And I'm like, no. I'm like, oh, do you want discounts? You know, up to 10% off, blah, blah, blah. I'm like, okay, here, all I need is your telephone number. So they put my telephone number in. Actually, that's it. They just put my telephone number in. They gave me the key. And then you have to go online to fill out the preferences. But it's a weak entity, so you can still use the telephone number and still use the account with or without the preferences being identified, because I was able to use it right there in the store. You know, when you ring you up and you just put your telephone number as your 10-digit employee, your 10-digit store card number or whatever. Why do people have to do that? I don't know. I think it's because they're trying to keep track of customers. I don't know. But then you're encouraged to go online, because if you go online and fill out the preferences that are associated with the ID that they just gave you, that's going to get your discounts, then you get the giveaways in the mail, you know, the free mailing stuff, you know, the coupons and stuff like that they're going to send you. Well, it's like Walgreens, or it's like all the stores around here, you got to give them information in order to get a discount on anything. And if you don't have it, they don't give it to you. Anyway, so going online and filling out preferences is a good example of that. I'm a customer. I have the account with or without the preferences that are associated with it, which means that this is going to work. It's a strong entity. This may or may not exist. I might be a staff and not have any dependents on the health insurance policy, and that would be non-existent. So here's our weak entity for preferences. It might be a preference type, a maximum rent. This is for properties for rent, it looks like. So you got the client over here with all this information. They may or may not state any of these weak entities. So if you keep weak and strong together, then that's when you get null, 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 null. You got empty table. You got tables full of junk because nobody puts anything in there. But you have to put something in there, so it's space, 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 space. You see it when people fill out forms. They go, okay, oh, you don't want to give in that? Okay, I'll just put in something. And they just start putting garbage in there. Then you got a database full of garbage. If you just make it weak, it doesn't have to be in there. Your account can still be active without the garbage. So here's a relationship called advertises with attributes. So we have a newspaper that advertises property for rent. So here's the newspaper, and we have a newspaper name, and then we have a property for rent with property number over here, and we have a dot, 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 dot. What is that? That's a relationship attributes. That's a list of attributes for relationships. So the relationship called advertises here with attributes. There's no entity associated with it. So relationships can have attributes. You want to put them in a separate box, and you put a dotted line here to show that it's from a relationship. If it weren't a dotted line, you'd have a diamond symbol in here, and it'd look like an entity, but there's no name. Instead, there's just the date, the advertising, and the cost of the advertising. Oh, we're going to sell this ad for $10, and that was for $20 or something. So we can have different ads with different prices, and that's going to be associated with this. Because this is really going to be 3 tables, because this is going to be multi-valued. Newspapers generally list more than one property for rent. If they didn't, then this property for rent would be an attribute of the newspaper. Here's our one property for rent, and we would have no relationship table. Instead, we would have this information and this information all in this table. And that's a decision we make when we start looking at cardinality, which is coming up next. So cardinality, you can't leave that out. Cardinality is the number of participating entities. Is it just one? Is it many? Because if it's one, it contains a single valued attribute. If it's many, you get multi-valued attributes that are associated with that. So now you can probably see why you need to practice this a little bit. If you don't, all this goes in one ear and out the other, and it's like 10 minutes later, like, what did we just cover today? Oh, entity relationship, what? Structural constraints. This is where I like to use the word multiplicity. You know, it's like multiplicity, like the movie Multiplicity. Except for the copies were never as good as the originals in that movie. You guys see that movie? Yeah. It's a good rental, actually. It's a good, like, you just need a laugh movie. When you feel you're overworked, just watch that movie. Main type of constraint on the relationship is called multiplicity. Multiplicity is the number or the range of possible occurrences of an entity type and may relate to a single occurrence of an associated entity type through particular relationships, represent policies, business rules established by the user or the company. So this is also called cardinality. Database people or math people like to call it cardinality. Movie people like to call it multiplicity. I don't know. Database theory calls it structural constraints. It's a constraint. It's a form of a constraint. The most common degree of relationship is binary. One entity having a relationship with another. So don't get degrees of relationships of participating entities confused with cardinality. There's a number of how many are participating in the relationship, and then how many times do they participate, which is like two separate concepts. The binary relationships are generally referred to as one-to-one, one-to-many, many-to-many. So we'll see some examples of those. Staff manages branch relationship, going back to where we started in the beginning here. We've simplified it now. We have a staff that has a staff number as a candidate key there, and it manages a relationship type. Manages, there's relationship 1 and there's relationship 2 with staff over here. This one doesn't manage anybody, but he's in the system. And we have branch over here, 003 and 005. So if we looked at the this is a one-to-one relationship. Even though we have 2 staff people, that's only one staff person managing one branch. So that's what I did. Don't get confused with the number participating along with the types. So here we have the one-to-one. So if we read it, it's common to see a colon here, 1:1, or 1:1. Means the same thing. Or just 1. When it's 1, it could just be 1. I like to just put 1. And then I'll put an asterisk for its many-to-many. 1-to-1, many-to-many. And then I'll do this if it's not more than 1. Up to 1 or 0 to 1. So you could leave it 0 or leave it blank, actually. If you leave it blank, it means it doesn't have to participate. This is where you get, and if we go back to the first assignment, there's optional and mandatory participation. That's the 0 or the 1. 0 is optional, 1 is mandatory. Optional participation means you may or may not have a relationship. 1 means, oh, you're going to have one, or you're not going to be in the system. So what do we have here? Each branch is managed by one member of the staff. So each branch. And it's funny because you read in opposite order. If I'm here at the staff, I go to branch first and I read back. And if I'm on the branch end, I talk about the staff, then I read about the branch. So it's kind of odd. It's because staff is having a relationship with branch. So each branch is managed by one member of the staff. So 1-to-1. And a member of the staff can manage 0 or 1 branch. So 0 or 1, which means it's optional. Staff people are optionally managers. Not all of them are managers. Some of them don't manage any branches at all. Some of them might be managers and not manage any branches. Some might just be staff people. So this is the number here called the cardinality or the multiplicity. Now we have staff that oversee property for rent. And then we have the relationships that go on here. We have this guy is overseeing 2 properties. He has 2 different relationships. This guy only has 1 relationship. And he has one with this one here. And then this property for rent is not being oversaw by anybody. And this staff person here is not overseeing anything either. So the multiplicity of this particular case is that it oversees 1 to many. So each staff person here, staff oversee property for rent. One staff might be doing 1 or they might be doing many. So 1 to many. Many takes into consideration of 0 or more, up to any number. So each property for rent is overseen by 0 or 1 of the staff. So on the staff side we have the 0. On the property for rent side we have the 1 staff member for 1 property. Or each member of the staff oversees 0 or more properties for rent. So 0, and they might not be overseeing anything, or more properties for rent. So we have the more as the asterisk here. And we have the overseas relationship of staff overseeing properties for rent. So staff here, and then properties for rent here, overseeing here. If we had a school bus, and the school bus had 25 seats, then the school bus would have 0 to 25 seats. Instead of using the asterisk, we could put the number 25 in there. Because it could never be asterisk. How are you going to get more than 25? You got a max. When you don't know the max, you want to leave the max open, you put the asterisk in there. It's a wild card. So it could be 0, it could be 25, it could be 50, anything you want. So newspapers that advertise properties for rent. So many different newspapers advertise many different properties for rent. Many different properties for rents are in many different newspapers. So you have a many-to-many relationship going on here. So I don't know any of these newspapers are all English. So we're all from England, looks like. So advertises. So here's the newspapers, and they're advertising, and this is for the property for rent. And we've got interesting phenomena here. We have a relationship with this one, and we have a relationship with this one. They're all for this property for rent. So it's multiplicity of many to many. So each property for rent is advertised in 0 or more newspapers. So we got 0, ... Or each newspaper advertises 1 or more property for rent. Because the newspaper's not going to have a property for rent section if there aren't any properties for rent. It's kind of like a waste of ink. Properties for rent, but nothing. Computers for sale, nothing. So they're going to have 1 if they're going to list it. So on the constructural constraint, the multiplicity for complex relationships, the number or range of possible occurrences of an entity type in an n array relationship, then when the other n minus 1 is the values are fixed. So when we have some sort of a number or a range, we can put the number in there instead of putting the asterisk. So we have 3 so what we've been seeing so far is a binary. Same concept applies towards 3, but we have to put a number. So the number goes next to the entities that's associated with. So now we have 3. This is where most people start getting, what? We have branch over here. So it looks like the 3 relationship with values for staff and branch entities that are fixed. So we have staff registers client at a branch. You remember that relationship? Let's just go to it. Multiplicity here. We've got staff who registers client at a branch, they might have 0 or more clients. So there might be some staff that doesn't have any clients. It's a bad day. It's a slow day at the office. No clients. Or they might have 20,000 clients. We don't know how many clients. We know that one staff person only works at one branch, and that one branch only has one staff person who's going to register one client or no clients. So we know by looking at this business rules that the client can't be registered at multiple branches. They're only registered at one branch, and they're only registered with one staff person. Multiple staff people can't register multiple clients at multiple branches. It doesn't work out that way. So it's a 1-to-1 all the way around, except for a 0 here on the client end, because we don't necessarily have to have any clients for this part of the relationship to hold true. We might be looking for new clients, or might be registering our first client. So the summary of the multiplicity in terms of the constraints, the summary and the ways in which we're representing the constraints. So alternative ways to represent the multiplicity, here's some here. And the meaning here, 0, ... 1, 0 or 1 entity occurrence, being or 1, 1 or 1, or just 1. That's why I say I just put 1. If it's 1-to-1, I just put 1. If it's 0, I just put 0. If it's many-to-many, just put an asterisk down. It's just shorthand. So 0 or many occurrences, 1 ... asterisk, 1 or many occurrences. 5 ... 10, minimum of 5 up to the maximum of 10 occurrences, or 0, 3, 6 to 8, 0 or 3 or 6 or 8 entity occurrences. So those 20 pages of reading on assignment number 1 is a review of all this stuff, all the rules and all the syntax. So if you're confused right now, don't worry, you got 20 more pages of reading you can do. And that'll tell you everything you ever wanted to know about this, plus more, actually. Structural constraints. So this follows in one form of database constraints. It's cardinality, meaning it's a multi-valued, it's a single-valued. It's a constraint we're putting on the database, and it's a structural constraint. So it's made up of 2 or more restrictions on relationships, cardinality and participation. So cardinality is what we've been talking about. It describes the maximum number of possible relationship occurrences for an entity participating in a given relationship. 1, 4, 1, n. It's the second of the series. The first of the series is the participation. If it's 0, it's optional. So it determines whether all or only some entity occurrences participate in the relationship, optional or mandatory participation. So here's yet another way of looking at it. With multiplicity as cardinality and participation constraints. So we got the cardinality. One branch is managed by one member of the staff. So then we have one member of the staff manages one branch. So the one is mandatory. We have to have one. All branches have to have one manager. If we're talking about the manager's relationship, the one is mandatory. So all branches are managed, mandatory participation on the branch. However, it's optional here. Not all staff manages a branch. You could be a staff member and not be a branch manager. So that's optional participation for staff. And the 0 is on the staff end. So we're reading on it on the staff end. So the 1 is a member of the staff. Why do we want to know about any of this stuff? Because when we translate those tables, anything multi-valued or anything, well, optional we can ignore actually, but anything multi-valued with the asterisk turns into, we do different things with the relationships. We get rid of the relationship when it's 0, 1 or 1, 1. There's no such thing as a table that's going to need to be connecting them together. Table's not needed. If there's only a single valued attribute, no need for a separate table for that. If there's a multiple valued attribute in any one of the participations, we look at who's participating in it and we create their table that goes between the 2 participating entities. And that's where we get our separate table that comes out of that. We'll see that when we translate tables in the next lecture. But, problems with the entity relationship model. Alright, so we've seen a brief overview of participation, optional and mandatory, cardinality, both single and multi-valued, relationships and entities, multiple degrees of relationships, and multiple relationships between different entities, which are the basic scenarios. And we've assumed that this order is up to you, and it is. You can put this on the left, you can put this on the right, you can put the arrow there, you can put it up and down if you want. What happens when you create the diagram is you run into these common problems. Let me show you what the common problems are. There's only 2 of them actually you have to worry about. You look for the 2 common problems and then you fix the diagrams to avoid them. So common problems may arise when designing conceptual database models called connection traps, often due to misinterpretation of the meaning of the certain relationships. Let's take a look at some examples. 2 main types of connection traps are fan traps and chasm traps. So these are 2 types of traps that end up happening. In your first variety, or the model, you represent the relationship between the entity types, but the pathway between the fan trap, certain entities, occurrence is ambiguous. There's a pathway, but we don't know which way it goes. We know there's a connection, but it's ambiguous. We don't know. Or we have the other one where we suggest the existence of the relationship, but there's no pathway. There's no way of getting there. It doesn't exist between a certain entity creation. So either we're missing the pathway, or we have the pathway, but we can't see it too clearly. We can't tell. So let's look at, we have the pathway, but we can't tell what's going on. Here's a diagram. It might look fairly normal to you. Staff. So a division. If I read this correctly, I started out with staff because that's how I normally do it, but I'm looking at the arrows going this way instead of this way. So we have a division that has staff. So one division has 1 staff manager, I guess. And one staff might work at multiple divisions. Okay. And then we have a branch, a division, actually. A division operates at a branch. So we have these divisions. They have staff and they operate at branches. And one division and one branch, and one division, one branch. One branch has multiple branches for one division, but it has to be at one division. Or branches might have multiple divisions. One division's only at one branch. That's actually how that's reading.
So one division is one branches.
Well, that's a problem. We can't tell. If we have multiple divisions at multiple branches, we don't know which branch. Here comes the question. Here comes the question. At which branch office does staff number SG37 work? So we have staff, and the staff here has a division, and this division D1 is at 2 different branches. We have division operates at branch B003, and we have division 1 operates with a relationship at B007, and we have SG37 that works at division 1, and we have SA8, but we're only concerned about SG37 for this question. We don't know which direction for which branch, because we can't tell the branch and the staff. What we don't do is this. It's missing. Well, it's there. It's ambiguous. There is a connection. There's a connection between staff and branch, and it's through the division. Problem is, we have a many over here. Many divisions. So branches, one branch can be at many divisions. And this happens to be the branch that the staff person is working at. Which branch are they working at? We don't know. We just switch the order. I'll show you the. We restructure it. This is for illustrative purposes. What we did was we just flipped them around. We changed the order of the boxes. So we know what division, the division here, and we know that the division operates at a branch, and the branch has staff. So now we have the connection between the staff and the branch. So restructuring the model resolves the fan trap. It takes away the ambiguity. Because in the previous example, the previous way we had this done here, the divisions themselves working at multiple branches, and this guy's working in the division. Well, which branch does he work at? It could be branch A or it could be branch B. Now we know the branches that have staff. We know who's working at each branch, and we know what divisions are at each branch. So from the branch perspective, we can see what division. I'm in division 1. So then we know from branch has division 1 in it. So we can go backwards through the operates. It's just a restructuring. Sometimes you have to restructure the diagram to get rid of the ambiguity. What does that do? Well, it restructures your tables too. It makes your keys different. Because what ends up happening is when we reduce this down, we get rid of the relationship by putting foreign keys inside of the tables. Every table has a primary key. Every table should have a primary key by default. Primary key is a way of uniquely identifying each entity occurrence inside of that table. What foreign keys do we need? That depends on the relationships we have established. In this particular case, staff is going to have a foreign key for the branch. And division is going to have a foreign key for branch. So it knows which branch. Without it, over here, staff is never going to have any foreign key for branch. You wouldn't know that. You wouldn't see it, you wouldn't build it. If you had this diagram set, you'd have, oh yeah, this staff is working in this division. But you're not going to arbitrarily put a branch in there. If you did, you're throwing darts. You're not reading anything from the diagram. If that's the case, you're making it up. Because you wouldn't. There's no relationship. There's no direct relationship, so there's no need for a key. Because the relationship is between division and branch. So why would you have a branch relationship? Why would you have a key in here? You'd just be guessing. But you'd have a division, but you don't know the division. You could actually get through this with extensive SQL query. It's not easily apparent, but you probably could query it if you had the correct information inside of the branch. So restructuring the model does this to us, gives us our branch first, gives us our division. It operates at different branches and then it has different staff. So it gets rid of putting the multiple on the end here, gets rid of it. So we know that he works at branch B003. Who knew? B003. So that's one of the common problems. You just reorder it. Here's our second common problem. This one it has to do with the relationships, actually. So we have a branch that has staff that oversees properties for rent. And the question is, we're missing an overseas. So on the overseas, we're missing something. We have a staff person here. At what branch office is property PA14 available? At what branch office is PA14 available? Don't necessarily know that information because we don't have a connection between the properties for rent and the branch office. Instead, this is why if you do binary to binary to binary, you end up with more tables than you possibly could imagine. All you have to do is combine the relationships and don't be afraid to go up to 4. 3, 4, very typical. Binary, problem after problem after problem. So here we got properties for rent. How do we know what branch? We don't know what branch. So we're going to fix the problem. We add a new relationship in here. If we add a new relationship, to remove it, adds the offers relationship. So what did we just do? We just turned that into a 3. But it's now, this is actually kind of dangerous to do. You could restructure it by putting offers in the middle. So you put the relationship in the middle, branch offers property for rent with staff. And you've got 3 going on here. So you've got branch on the top, offers in the middle, properties for rent with staff. Or you could do it this way. It doesn't really matter. It's your drawing preference. I don't like to see it this way. This is just a fix on the original. I would put that in a 3-degree relationship is what this really is. But before it was only a 2-degree. So we turned it into a 3. So the branch has staff that oversee properties for rent, and the branch offers properties for rent, which is 3 participating entities all in the same relationship, and the relationship is offers. So it's a restructure to get rid of the problem. So now it looks like this. We can't get it through this way, so we get it through this way instead. We just added another relationship in here so we can connect them. This I'd call more challenging. It's easy to draw the diagrams. When you look at the diagrams, it's hard to find the problems until you start asking the questions. And then after you build the tables, you figure out, oh, I can't figure out what property for rent's at which branch. Oh. And then you start building and you start adding things. And it's helpful to go back to the diagrams, change the diagram, and then change the tables to modify the table structure to match the new diagram because you had a mistake in the diagram. So that's why I say it's more of an iterative process. So restructuring the model, now we remove the trap. So if we compare the symbols, take a look at the symbols here. This is 1, 2, 3, 4 different techniques. I kind of have a tendency to use the crow's feet actually. In fact, this is the one that's being used in the 20-page write-up for the assignment number 1. It's a little bit more challenging. This one here is not too bad either. Not too bad as a diagram symbol set. Use the symbol set options that are available for you in the tools that you download. So all the tools don't have the same ones. Most entities are represented in the form of these rectangles. Most of the relationships are lines. The diamond is pretty much the universal. Diamond is universal symbol for the relationship. You don't have to use the option symbol. You can get away with that. Or the one or more symbol. You don't necessarily need that. A lot of people put N or M. N stands for any number, and M stands for many. Well, it's different between any number and many syntax. Basically, they both mean the same thing. The assignment will go N for any number, colon 1, N, asterisk, N, something. Because that's the old way of doing it. And then people want many. Okay. Weak entities generally look different than the strong entities. You have, this is pretty popular here. You cut the corners off. That means there's an entity inside of an entity. Or here, the entity inside of the entity. It means that there's a composite. If you see the weak entity, you see the double entity going on, you know there's a composite because there's 2 or more entities involved with that key. It's a composite key that's going to be used. Here's some components. So we have relationships. So an entity school that operates, and we have the 1 to M in many different departments. Many different departments at a school. One school might have many different departments. A department has many students in it, hopefully, and department employs many professors, and departments offer many courses, 1 to M. A professor is an employee, 1 to 1. You can be an employee and be a professor. Yeah, you can be an employee and be a department chair too. And I don't know what else I am here, but I have multiple employments. I have a recursive relationship at ITU. So our employees have recursive relationships because I'm an employee, but I'm also department chair, but I'm also an employee. And I'm also a teacher. I'm also an employee. Actually, I think I'm staff too, actually, but that's a different story. Teachers, chairs, students enroll in many. So we have, people don't like M to M, or they don't like asterisk to asterisk. I'll just put asterisk down, or I'll just put M down or N down. Whatever you use is fine. Usually when there's an n, it means there's any number, meaning that there is a fixed amount. It's not infinite. The m generally implies infinity. So if it's many, it could go on forever. If we only know we have between, well, how many sizes of the rooms do we have? How many classes? We know that we have an average of something or other. It's a number, but we don't know what the number is. It means it's countable, theoretically. So, I believe it's time for a break. We haven't had one since lunch. Bio break, but I wanted to get through that. So we'll take a bio break, and then we'll come back for part 2 of this. Yay! Okay.